Okay, now let's try to prove this Bohr-Molera theorem. So 7.13 Bohr-Molera theorem. Okay, so let f be a function defined on 0 infinity, a real valued function, a real variable function, such that f(x) is greater than 0 for all x greater than 0. Suppose that f has the following properties. A, log of f(x) is a convex function. B, f(x) plus 1 is equal to x times f(x) for all x. C, f1 is equal to 1. Okay, this is normalization. This is essential property. This is another essential property. Two essential property plus normalization. Then f(x) is equal to gamma of x for all x. Okay, so this is like the factorial property. If you have a logarithmically convex function satisfying the factorial property, then it is the gamma function. Okay, so let's see. We will see the proof. By property B and C, by the property B and C, we can see that the f of x plus n is equal to x plus 1, x plus n minus 1, fx. Right? You just iterate by b several times for every non-negative integer, every non-negative integer n. So if we have fx equal to gamma of x, not for all x, only for x between 0 and 1, and then you're going to just add 1, add 2, add 3, because this part you have x between 0 and 1, but once you add it by a natural number, you can kind of move it to you can move the definition to other intervals. So this equation will give us this equation. Will give us that fx equal to gamma x for all x. Okay, so you just kind of shift it. Remember that after shift you will have the identical stuff, because this property is also a property of a gamma function. F satisfy this, gamma function also satisfy this. All right, next Next. So we are going to focus on the interval 0 and 1. So let x be between 0 and 1, and n is a natural number, n is greater than or equal to 2, an integer greater than or equal to 2. All right. Here we have to, okay, let me see. We have to borrow an exercise which we didn't prove. Let me see where we can get. Hold on a second, please. So we'll borrow the exercise on page 137, exercise 3.3, exercise 3.3. Okay. And what we have that the following inequality. Let me copy the inequality down. The other one. Okay, so this is the property. This is the result we need. What is the exercise 3.3? The exercise 3.3 is that if you have a convex function. Okay, so exercise 3.3, f is convex. If and only if, see here, we have this result. Let me see. If and only if there are three cases. There are three situations. B, a less than or equal to a, x less than u less than y less than or equal to b. This gives fu minus fx over u minus x less than or equal to fy minus fx y minus x. Okay, so you see here it's shorter. If the distance is smaller, then it will be less. And the slope, you just always imagine the slope. Slope is smaller. C, a less than or equal to x less than u less than y less than or equal to b gives fu minus fx over u minus x less than or equal to fy minus fu y minus u. So this is exercise 3.3. So let's see. We apply this property to this result, because x is less than 1, so it is between like the distance is smaller. The distance is smaller. So here you are going to use this the first part. You are going to have n minus 1 less than n less than x plus n less than 1 plus n. Okay, so the first inequality, 1 is based on the C, part C, right? Part C. So n minus negative n or negative n minus n, it doesn't matter. And x plus n minus n. So it's based on part C. So u minus x, y minus u. Okay, and the second part is here. Is this 2? Is based on, I see, again, let's write it. So x plus n minus n and 1 plus n minus n. See, that's exactly b. It's based on b. So if you know how to, if you prove this exercise 3.3, you just apply them to this situation. You will get this chain of inequalities. Those two inequalities are based on b and c separately. They're different. Okay. 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 Very good. Because of this this condition and plus a normalization, we know that f of m is equal to m minus 1 factorial for all integers m greater than or equal to 1. fm plus a normalization condition C, condition C. So let's see what we have. This is a negative one. Remember, this is a negative one. This is a positive one. So we simplify, not simplify. We compute this left side, the right side. We will get negative n minus 2 factorial, natural log, my bad, natural log, plus natural log n minus 1 factorial less than or equal to log f x plus n minus log f of n. F of n is n minus 1 factorial over x less than or equal to log n factorial minus log n minus 1 factorial. All right? Okay, so factorial is a product. Natural log changes the product to the sum. So this difference is exactly, or in other words, log b minus log a is log b over a. So n minus 1 factorial over n minus 2 factorial is a log n minus 1. No factorial. And its x is positive, we multiply this inequality by the positive. Log f x plus n and minus log n minus 1 factorial and less than x log n, x log n. Right? X log n. And then we are going to move this this term to two sides. So we will get log n minus 1 factorial plus log n minus 1 to power x less than or equal to log f x plus n less than or equal to log n minus 1 factorial plus log n to x. Okay? And we apply the exponential function. We will get n minus 1 factorial n minus 1 to power x less than or equal to f x plus n less than or equal to n minus 1 factorial n to x. N to x. Okay? So fx plus n, this, where is it? Okay, here, this is fx plus n. Fx plus n. So you apply this, you will get what? You will get n minus 1 factorial n minus 1 to power x over x plus 1 x plus n minus 1 less than or equal to fx less than or equal to n minus 1 factorial x to n x plus 1 x plus n minus 1. Okay. Right? So we have this. We have this. This part we don't change. This part. Here's n minus 1 factorial. I'm going to multiply it by n top and bottom. And here, this is x plus n minus 1. We're going to multiply x plus n from top and bottom. This n is combined with n minus 1. This x plus n is combined with x plus n minus 1. So we have we have that n minus 1 factorial n minus 1 to x plus 1 x plus n minus 1 less than or equal to fx less than or equal to, this is n factorial n to x. You see, every place you have n minus 1, you write n. x plus 1, you see n minus 1, you write n. And this xn is on the top, this x is on the bottom, this n is on the bottom. Okay? So this is clearly a standard form of squeeze theorem. A standard form of a squeeze theorem. And we know that we are going to let n approach infinity. Right? We are going to let n approach infinity because fx does not depend on n. Fx does not depend on n. You put whatever n here, you still have fx. So by letting n approaching infinity, remember that this is the Gaussian formula. Remember what is a Gaussian formula? The Gaussian formula. The Gauss formula. Gamma of z is limit n approaching infinity n factorial n to z, and then z plus 1, z plus n. But here we just use z equal to x. Z equal to x. So when n approaching infinity, this is a gamma of x equal to fx by the squeeze theorem. By the squeeze theorem. And this term is, the limit is 1, so it does not bother. The limit is 1. X is between 0 and 1. Okay? So we finished the proof of the Bohr-Molera theorem. Bohr-Molera theorem. Okay, so we are done. It's a very, very neat proof. The is not essential, but one of the important key step is this step. One of the important key step is this step. This step, we highly depend on the logarithmically convex function property. Logarithmically convex function. Okay, convex function again, like this. So basically, they just ask you the slope. The slope is always increasing. The slope is always increasing. That's a property. Convex function slope becomes an increasing function of the secant line. Okay? Cool. Okay, so let me see. Yeah. There's several interesting properties so far. Let's see if we can do some of them. Okay. Again, this Bohr-Molera theorem is just for the real case, but it doesn't matter. You just replace x by z, you will get a complex gamma function. So we just say that the gamma function is uniquely determined by the factorial property plus logarithmically convex function. Okay, logarithmically convex function. Gamma function is one of the most important functions. So it has a lot of results. Here there's another result. If the real part of z is a positive, then the gamma of z can be written as the integral from 0 to infinity e to negative t to z minus 1 dt. Okay, e to negative t to z minus 1. Okay, so this integral is very bad. Okay, this integrand behaves badly at infinity and 0. T equal to 0, t equal to infinity, it behaves badly. Okay, so we are going to show this is correct, but in order to show this correct, we need some lemmas. We need some lemmas in order to eventually prove the theorem 7.15. Okay, so now let's see the lemma. What lemma we need? So let S be a set of complex numbers z. A is between the little a is less than or equal to the real part of z less than or equal to capital A, where a is less than a less than infinity. Okay, so we do have some band, vertical band. Because here, you see here, this t will, z, yeah. Let's focus on this band. Okay, the result. For every epsilon greater than 0, there is a delta greater than 0 such that for all z in S, for all z in this vertical band, the obvious value of alpha integral from alpha to beta e to negative t to z minus 1 dt is going to be less than epsilon whenever 0 less than alpha less than beta less than delta. So basically we're handling 0 point. When alpha beta very tiny, then this is going to be less than epsilon. The integral is less than epsilon. It sounds like the Cauchy condition about the convergence. Cauchy sequence. Remember Cauchy sequence. There is a capital N such that when mn greater than capital N, the difference between m and n, xm minus xn is less than epsilon. Okay, so it sounds like the Cauchy sequence. Here's alpha and beta are both small. Okay, this is the case when we have 0, and for every this is part A, part B, for every epsilon greater than 0, there is a number k such that for all z in S, the absolute integral from alpha to beta e to negative t to z minus 1 dt is less than epsilon whenever beta is greater than alpha greater than k. So this handles infinity. This is about 0. This is about infinity. Okay? 1 is 0, 1 is infinity. Well, very good. Now let's prove them. Here is a lemma. Lemma, we mentioned them, but we're going to give the concrete proof. So for A, if t is between 0 and 1, if you have t between 0 and 1 and z in S, t between 0 and 1 and z in S, then what we have, you see here, we have something like this. The real part of z minus 1 times log t is less than or equal to a minus 1 times log of t. Why? This whole thing only because log t is negative. Log t here, log t is negative. T is less than 1, less than or equal to 1, so it's less than or equal to 0. Without the log t, it's a real part of z minus 1. It's greater than or equal to a minus 1, but times the negative number is less than or equal to. Okay? And exponential e to negative t, of course, negative t is less than or equal to 1. Less than or equal to 0. So it's less than 1. Less than or equal to 1. Okay? Less than or equal to 1. So now let's estimate e to negative t to z minus 1. It is going to be less than or equal to t to the real part of z minus 1. The real part of z minus 1. Okay? And this one is less than or equal to t to a minus 1. T to a minus 1. This okay. Yeah. Okay. So this part we have inequality simply because e to negative t is less than or equal to 1. If you do only have this, what is a to x? What is a to x? A to x is e to x log a, right? E to x log a. And you only need the log a is a positive number. A is a positive number. So you only need the real part. Remember, exponential function, the norm is only depend on the real part. So it's e real of x log a. So this is a to the real part of x. So whenever you have ops value of an exponential function, it's always a to the real part. If you want, you can use z to emphasize it's a complex number. Okay, so this real part z minus 1, t to real part of z minus 1 is exactly the ops value of t to z minus 1. But this inequality comes from e to negative t less than or equal to 1. Okay, so if we have alpha beta with this relation, alpha less than beta less than 1, then we have integral alpha beta e negative t tz minus 1 dt less than or equal to this, and this one we know what it is. It's a beta a minus alpha a. It's power function for all z. In S, all z in S. Okay, all z in S. And this condition is not that artificial, because remember that for the statement of a lemma says every epsilon there is a delta, so that this is less than epsilon. So if this delta is too big, is bigger than 1, you just choose a smaller delta. If delta is smaller than 1, in this integral, t is always less than or equal to 1. So it's not too bad. Well, what do we have? Okay, we have this. For this is concrete real functions. So for epsilon greater than 0, we choose delta between 0 and 1 such that 1 over a beta to a minus alpha to a less than epsilon for beta minus alpha less than delta. Continuous function. Always do it, right? Continuous function, you can always do it. So you prove part A. Part A is done. Part A is checked. Okay, now let's check part B. Let's check part B. For part B, remember we're going to push t to infinity, so t will be very large. So for z in S in t greater than or equal to 1, z in S t greater than or equal to 1, then t to z minus 1 ops value less than or equal to t to equal to. So first let's put equal to the real part of z minus 1 and less than or equal to t to a minus 1. Remember we have vertical band, finite vertical band. So it's less than a minus 1. Okay, and this t to a minus 1 exponential of negative 1/2 t is continuous. On the interval 1 infinity, and converges to 0 as t approaches infinity. It's sure, because this thing grows faster. Exponential function grows faster than any power function. So there is a constant c such that t to power a minus 1 exponential of negative 1/2 of t will be less than or equal to c for all t greater than or equal to 1. Bounded. Basically, we say it is bounded because it converges to 0. Okay, then we have e to negative t to z minus 1 is going to be less than e to negative 1/2 t to z minus 1 times e to negative 1/2 t. This is equal. And then we have inequality c e negative 1/2 t. C e negative 1/2 t. It doesn't matter what the rational number you have here. You always have this, right? So for all z in S and t greater than or equal to 1. Okay, very good. So for beta greater than alpha greater than 1, we have this value integral from alpha to beta e to negative t to z minus 1 dt less than or equal to c times integral alpha to beta e to negative 1/2 t dt. It is equal to 2c e to negative 1/2 alpha minus e to negative 1/2 beta. Okay, so again, for any epsilon greater than 0, there is a k greater than 1 such that 2c, this whole thing, e negative 1/2 alpha minus e negative 1/2 beta less than epsilon whenever alpha beta greater than k. Okay, alpha beta greater than k. Whenever you have this, you always get it. And this one, remember this one, there's no uniform continuity. Well, it is still uniformly continuous. Yes, but you actually just drop 1. You drop 1, you can use alpha or use beta. Use a smaller number, that's enough. Anyway, figure it out. So part B is proved. Part B is checked. All right, so this whole thing exactly gave us the so-called uniform convergence of the integral. The uniform convergence of the integral. Okay. So let me write down what the author wants to say. So these result exactly mention the concept of a uniformly convergent integral. For example, if we consider integral from alpha to 1 e to negative t to z minus 1 dt, if we consider this for alpha between 0 and 1, the part A, say that the integral satisfies some Cauchy criterion, a Cauchy criterion as alpha approaches 0. Cauchy criterion as alpha approaches 0, right? Okay, and Cauchy criterion, like what I said, 2 point for any epsilon there is like a point, the delta, such that when alpha beta are both less than delta, then you satisfy certain property. And the part B is for the interval, this interval from 1 to alpha, e to negative t to z minus 1 dt. It's about convergence, right? You see, this is, if you consider this as a x, I don't know that's, okay, this is x alpha, then the x alpha minus x beta, x alpha minus x beta is from alpha to beta, yes. Yeah, it's like this. So you can see this is exactly the Cauchy criterion. And this one is from the part B for alpha greater than 1. All right, so that's a dilemma before we prove the theorem 7.15. Okay, so we will stop the video at this point and we will continue the discussion. We are not done. We are going to continue the discussion about this formula and prove the 7.15. Okay, prove the 7.15. Okay, thank you.